Welcome everybody. Today we are going to talk about the stability of the control system. Previously we talked about the transit response of control system, and we highlight two types of the systems, which is the first order system and the second order system. We learned how to find the parameters of the performance of the control system from the first order and also for the second order system. Today we start with the stability at the second design criteria of control system. We said we have three design criteria. First is transient response, second is stability, and the third is the steady state response. So stability is the most important performance criteria. And actually, if the system is not stable, no need to discover or to investigate its transient response or its steady state response. So the unstable system actually cannot be designed for specific transit response because it's already unstable. So you can see in the figure here, this like stable, this is neutral, and that one is the unstable. Unstable means can be changed from stability to instability at any point. So we need to define three type of stability. So the first type is the absolute stability. So absolute stability means the system can be either stable or unstable. There is nothing in between. Either the system is absolutely stable or absolutely unstable. Okay. The second is the relative stability. After we found our system is stable, we need to know the degree of the stability. So if the system is stable, how for what the degree of stability? Is it 100% stable, 90% stable, or 50% stable? It depends on what's the degree of its stability. Okay. The third type is bounded input, bounded output stability, BIBO. So that type, actually the bounded input, bounded output depends on the input to our system. So the system will be stable for specific input and unstable for other inputs. Okay. We mentioned before, that means we have two type of response. Force response, which is generated by applying input to our system, and natural response, which is generated by the component or the transfer function component of the control system. So for example, for electrical system, we have electrical system component like resistor, capacitor, inductor, and so on, operation amplifier. So this component will generate the natural response because these components are used to find the transfer function of the control system. While the force response actually is generated due to the applied input to the control system. So if we have pulse function, for example, or unity function applied to the input of our system, so we are going to add more pulse, which is responsible to generate the force response. In terms of the natural response here, the system is stable if the natural response is reached to zero. So if the value of the natural response close to zero, so that means the system is stable. Okay, so we already mentioned before, we said we need to make the natural response close to zero. In this case, we can reach to our system stability. The system is unstable if the natural response approaches infinity. So the natural response is very high, cannot goes to zero. So goes to infinity. For this case, we call it the system will be unstable. The system is marginally stable if the natural response neither decays or nor grows. So the natural response like stable. I mean the value of the natural response is stable, not change, or steady. That means can, not go up, not go down. So the system we call it is a marginally stable. So there is natural response, but this natural response is like fixed or more stationary, so no increase, no decrease. So in this case, we call our system is marginally stable. The second way to calculate the system stability, also using the total response, which is based on the bounded input, bounded output. So the system is stable if every bounded input yields a bounded output. So for every input we apply to our system, we are going to get a specific output. Okay, but the system will be unstable if any of the bounded input cannot yield or cannot yield a bounded output or will give you unbounded output. Okay, so based on the natural response, we have stable, unstable, and marginally stable. This depends on the natural response, depends on the component of the system, and the other one is based on the input and it's more related to the force response because the force response is depends on the pulse of the signal of input to the system or of the input signal to our system. Okay. The pulse and system stability here. So what's the relation between the system pulse or the transfer function pulse and the system stability? Actually, the location of the pulse will determine the system stability. So based on we said our transfer function, for example, GS is consists from or is equal to output CS over input, which is RS, correct? So this can be some values here for the output, for example, S plus 2, for example, now, or S square plus S plus 3, and so on. So it consists from numerator and denominator. So the numerator here is responsible to generate the zeros, which make your transfer function equal to 0, and the denominator here is responsible to generate the poles. And the pools here that we are going to talk now is used to determine the system stability. So based on the pools of the characteristic equation of transfer function, we are going to decide is our system stable or unstable. So when the system will be stable, the system will be stable if the pools of the closed loop, we are now talking about closed loop, not about GS. GS is the open loop transfer function, but the TS is the closed loop. So from now and forward, when we are going to determine the system stability by using the method of Routh table here, we are going to find the closed loop transfer function. And we said, for example, for the feedback system, as we mentioned in chapter 3, we said feedback system equivalent of transfer function here will equal to GS over 1 plus GS HS. Okay, so this we call it the closed loop transfer function of the feedback system. So you have open loop, you have closed loop. Now we are going to talk about the closed loop. So the system is stable if the system has poles on the left half plane. Left half plane, that means you are going to draw this one. We already learned before how to represent the control system by using the S-plane. So the S-plane here will consist from the four quarters, Q1, Q2, Q3, and Q4. Okay, so from 0 to 90 represent Q1, from 90 to 180 represent Q2, from 180 to 170 represent Q3, from 270 again to the 0 or 360 is equal to or is Q4. So the place of the poles which will be defined in this S-plane will decide if our system is stable or not. So for example here, if your poles are, if you have two poles, for example S equal to positive 1, S equal to positive 2, so that means the poles will be located in this area on positive 1, positive 2, so it will be on the Q1, correct? It is real poles and also positive, so it will be placed on the area of Q1. So since it is only real numbers, it will be placed on the x-axis here or the positive x-axis. If your poles are negative 1, negative 2, for example, that means it will be located on the Q3 or Q2 or on the real axis of the negative part of S. If your S is imaginary number, that means it is J5, j negative j5, so it will be located on either the positive imaginary axis or the negative imaginary axis. So it will be on the axis here. So this will be imaginary numbers. Here we have real numbers and distinct number. Okay. If the poles are located or are complex numbers, so it will be located in this area, for example, or this area here, either in Q1, Q2, or Q3, but it has two parts, which is real part and imaginary part. So in this case, the it will be distributed inside these quarters. Okay, so now if we have a transfer function open loop, we need to find first, we need to find its closed loop transfer function by apply the simplification method that we learned before for the feedback control system. Okay, then we find where is the poles are located for this transfer function. Okay, after we define where is the poles, we can decide if this system is stable or not. The system will be stable if its poles or its poles are located on the left half plane. So it will be on the left half plane, means on this is the imaginary axis. Anything if the poles are located in this area to the left, so the system will be stable. If the poles are located on the right half pole half plane here, if the poles are located at the right half plane, so on the right side, I mean greater than zero, this is the zero axis, correct? So this is the 0 point. If the poles is here in this area, whatever is a positive or negative, it means in any place here, so our system will be stable even if there is only one pole located in this area. It doesn't mean all poles should be on the right. No, if you have only one pole located on the right half plane of the S plane coordinates here or representation, the system will be unstable. So this is unstable from 0 and forward to the infinity positive, here from 0 to the infinity negative, the system will be stable. Okay, so this is how we can define the system stability by identify the number of poles and the location of poles. Okay, then we have one more case, we call it marginally stable, that we mentioned before. Marginally stable, we said the system is not absolutely stable, the system is stable for specific input only. So if we change if the poles is changed either a little bit go to the right, it's become unstable. If the poles go to the left, it will become also stable. Okay, so on the right will be unstable, on the left will be stable. That means the poles will be located on this axis. Okay, so if you have your poles located on the imaginary axis, that means your system is marginally stable. Why? Because if the pole is moved a little bit to the right, it's become unstable. If the pole is moved a little bit to the left, it's become stable. So this we call it marginally stable system. Okay, so this is how we can define or how we can identify system stability based on its poles location. The system stability criterion here can be found. Actually, we do not need, in order to define the system is stable or not, we do not need to know the exact place of the pole. We can just know, is it on the left side or on the right side? We have this, the S plane. If the pole is located in this area to the right, so it will be unstable. If the poles are located in that area to the left, will be stable. If the poles are located on the y-axis or imaginary axis, the system will be marginally stable. So we do not need to know where is the pole. Is it at 5, at 4, at 3? No, it's negative. If the pole is negative, so the system is stable. If the pole is positive, so the system is unstable. If the pole is imaginary, that means is located on the imaginary axis, so the system is marginally stable. How we can or which poles we are going to talk about? We said we are going to talk about the poles of the closed loop transfer function. And when we said closed loop transfer function, that means we need to define what is the denominator of the transfer function. So this is TS, not GS. TS means closed loop. TS is used to define the closed loop transfer function. GS is used to define the open loop transfer function. So the TS here, whatever do you have here, s to the power of 5 plus s to power of 4 plus 3s cubic plus 2s square, for example, plus 1 plus s plus 1. This actually is responsible to decide is your system stable or not. Okay, and here this equation actually of the denominator, we call it the characteristic equation. So the characteristic equation here represent the equation or the values of the QS represent the denominator of your transfer function. So this is the transfer function zeros. BS is responsible for zeros, and this one is responsible for poles. This one for zeros. Okay, so sorry. So poles are the roots of the QS. That means you are going to take this equation, you put it equal to 0, then you solve this equation to find the value of S. If you have S to the power of 5, that means you have 5 solutions. If you have S to the power of 4, you have 4 solutions. If you have S to the power of 2, you have 2 solutions, and so on. Okay? So you are going to find the roots of this equation. After you find the roots, you are going to say, oh, our roots all negative, so our system is stable. The roots, there is one is positive, so the system is unstable. So this is this one example to show how the system or how the place or the location of the pool will affect the system stability based on a specific input here. So if you compare the two transfer function that you have here, if we call this one G1S and that one is G2S, okay? So we have two transfer function, two open loop transfer function. This is GS, this is G1S, this one G2S, and the two transfer function or the two system has or have a feedback. So this is the feedback. Actually, there is a feedback, and the value of HS in this case equal to -1 or equal to 1, actually 1 then multiply by negative, so it will be -1. H here also HS, which is the feedback H2. If we call this G2, this H2, this G1, this we call it H1, for example. So H2 equal to 1 also. Okay, both are negative feedback. So since it is negative, so we call it negative feedback. If it's positive, it will become positive feedback. So if I ask you now, which of these system is stable and which is unstable, you said, oh, both they have the same transfer function. This is G1, this is G2, but the values of the G1 and G2 here, the pools are the same. How many pools do we have for the first function? We have 3 pools. How many pools for the second transfer function? Also, we have 3 pools. If we are, if we say the stability is depends on the pool's value, not on the zero. So 7 3 doesn't make any sense. Okay, 3 7 here represent the gain for transfer function. It's not a zero, but it represents the gain of the transfer function. But if I ask you now, what is the pool for the first function? The pools here s equal to 0, s1 equal to 0, s2 equal to -1, s3 equal to -2. Okay, this is s equal to 0, s equal to -1. This is the pool. Pools means the value which make the denominator of transfer function equal to 0, so the transfer function become equal to infinity. If you have this one is 0, so 3 over 0 will be infinity. Okay, so the pools are the value of the roots which make your characteristic equation equal to 0. So this equation become equal to 0. If the denominator equal to 0, then the overall transfer function equal to infinity. Okay, so how many pools do we have? We have 3 pools, one at s equal to 0, one at s equal to -1, one at s equal to -2. Okay, so this is for G1. How about G2? For this transfer function, how many pools? Also, we have 3 pools, we have S1 equal to 0, we have S2 equal to 1, negative 1, we have S3 equal to negative 2. You will say, you can see here, both transfer function or both system, they have the same number of poles for open loop transfer function, which is G1 or G2. I mean G1 or G2, they have the same 0, 0, negative 1, negative 1, negative 2, negative 2. So why we said this system is stable while that system is unstable? This is the justification why we need to find the closed loop transfer function. When we say closed loop, means this is open loop. Open loop, almost the same. They have the same poles, 0, negative 1, negative 2, 0, negative 1, negative 2. But if I calculate the closed loop, the value of the gain here will affect the closed loop transfer function. So I will got different transfer function for the closed loop. If I have different transfer function, also I will got different pools. So the pools for the first, if you try to find what is the closed loop transfer function for this feedback system, it will be like that. You just apply this formula. Ts here will equal to G1S over 1 plus G1H1. Okay, just substitute for G1S by this value 3 over S plus 1 S plus 2, and you got it here. You substitute here again, and the value of H1 equal to actually 1. You just solve this one, find the T1S, and the same do to find the T2S. T2S here will equal to G2 over 1 plus G2H2. Just simplify like we did in chapter 3. Try to find the feedback transfer function here. When you find the feedback transfer function, for sure you are going to find different roots or different pools. So the pools for the first function, which is T1 here, will be located at negative 2.67, negative 1.6 or 0.164, and also you have two imaginary pools located at 1.047 J or negative J 1.47. So you have four pools. Actually, when you this transfer function will become or will consist four pools, two real and negative, two imaginary on the x-axis. Since our pools all on the left half plane, so here this is left half plane, this is left half plane, this is on the imaginary, so it will be marginally stable at this point. Okay, so the system is stable here. We do not have any pools on the right side, no pools here in this area, no pools. Okay, so the system is stable in this case. If you solve this T2S, you find the closed loop transfer function for this system, you are going to find four loops also. These loops are at this point negative 3, but you have another loop at positive 0.04, and you have two loops on the imaginary axis. Since you have one pool on the right side here is positive, on the right side or on the right half plane, okay, since you have one pole, so your system will be unstable even if it's one of four, so your system is unstable. And you can see how the response of these systems looks like up down up down up down, so there is no stability. But this system actually is go up to the big value, then go for to become stable until at t equal to infinity. So this is how to find or to define the system stability based on the location of poles. And you should know now, or you should understand that don't find the poles location for the open loop transfer function like G1 or G2. No, you must find the value of T1 and T2 first, which is the value of the closed loop transfer function. Then you can decide is the pole on the right or is the pole on the left and so on. Okay.